Okay, so I'm going to go through this. For this week, I'm just going to go through the homework assignment. But in other weeks, what I'm going to do is I'm going to sort of give another lab. And the lab won't be an assignment, nothing that's due, just something that I can sort of walk through the basics of whatever it is we're talking about that week, at least programming wise. Okay, so just a little bit of an overview. A Python notebook is a collection of cells, and each cell is either going to be a text cell or a code cell. So this right here is a text cell. If you want to edit it, you double click, and you have this markdown language. You can use LaTeX and things like that and this as well, and we'll see that down here below. To make it look like, you sort of get a preview of it right here, but to make it look like the text, you just run the cell. Which, if it's a code cell, there's a button that says like play to run. But if it's something like this, you can just do Shift Enter. Okay, and if you look here, I notice that we have a whole bunch of LaTeX there that we're using as well, and then Shift Enter to run this. So this is the first code cell. Now, the reason I'm using Python notebooks for something like this, well, there's two main reasons. One is very good for like telling the story, which is what we're going to be doing. You know, in the midterm, there's going to be sort of a narrative that's happening. Now, there's going to be quite a lot of like coding that gets done, and typically, I would think that coding should be done in like in a different file completely, rather than in the notebook, and then you have it in like an actual Python file, and then you just refer to it and call it in the notebook. But I actually want to see your algorithms and stuff like that. So that's why we're doing a little more like coding and programming and algorithms in the notebook rather than just using things. Another reason that I like to use the notebooks is because it is sort of a self-enclosed environment. You don't have to download something onto your computer and make sure that you have the dependencies and the packages and all of that sort of stuff installed as needed. Okay, so here's what we're going to do. I actually was working on this before, which is why you already see some work done here. So let me try to make it back to what it was. Something like this. So I just ran it, and each time you run the code, when you run the code the first time, it's doing all of these import statements. So by the way, what are all of these import statements? Well, these are the way that we import statements, import different packages to Python. So the main packages that we're going to be using are going to be NumPy, Matplotlib, and another one called SciPy that we haven't gotten to yet. Okay, so these are just packages that have a lot of functionality in them. If you are used to programming in C, for example, these are going to be sort of similar to the include statements that you would have in a C program. Okay, so the first thing is I need to store these two vectors in memory. So one way to do this, which is not the right way, would be to say v1 is equal to an array 1, 0, 2, and v2 is equal to an array which is minus 1, 2, 0. Okay, now why is this not the right way? Well, we really want something very simple. So Python is a high-level language, and the things that you want to be able to be true in terms of code almost always is true in Python. So we want to be able to write something like v1 plus v2, and we want this to give us the output of the sum of these two vectors. In other words, 0, 2, 2. But notice what happens if we run this code. It gives us this vector here, which is just the concatenation of these two vectors. So an array is sort of more or less a default Python data type. And the default definition for two Python arrays, when you add them, the default definition of that is to concatenate. So NumPy is a wrapper class for arrays. So we're going to do this, np.array, and it just adds functionality to the standard array functions. And now it has overloaded the operator plus, and now the operator plus is the exact thing that we want it to be, which is just the component-wise addition, and that's exactly what we get here, 0, 2, 2. Now, there's sort of a, a matter of taste here that we want to think about. Right now, we're storing v1 as an array. So I'm going to do something here. I'm going to do the following. I'm going to print v1 dot shape. So this should give us the dimensions of v1. Now we expect that this is either going to be 3 by 1 or 1 by 3. Now we're really expecting it to be 3 by 1. That's what we want it to look like. But notice what's going to happen here. So the shape is 3 comma. 3 comma. In other words, it doesn't have a well-defined second dimension when we have something like this. So there's a couple of things that we could do. We could either keep it like this, and it will not be a big problem until we get to the next part, or the part after this, which is what we're just about to do. But here's what I'm going to do. I'm going to use the reshape function in NumPy. So I'm going to say this. I'm going to say v1 is equal to v1 dot reshape, and I'm going to say that I want the new dimensions to be 3 comma 1. Now what this does is it says, okay, v1, Python is object oriented, so let's back up a second. Python is object oriented, v1 is an object, and NumPy arrays know how to reshape themselves. And it's going to say, you give me the new dimensions 3, 1, I'm going to reshape myself so that I have 3 rows and 1 column in kind of the best way that I can do that. So v1 is going to be equal to v1 dot reshape. Okay, and then similarly here, I want v2 to be equal to v2 dot reshape, and it's going to reshape it, and now it's going to be a 3 by 1 matrix. And so now we're going to look at what happens. So I'm going to print v1 before the reshape, and then I'm going to print v1 after the reshape, and we'll see what the differences are. So this is v1 before the reshape, and this is v1 after the reshape. So this is a matrix, and the notation in Python is that outer brackets are the enclosure or the boundaries of the matrix, and then each individual bracket here is going to be a row. So the first row is 1, the second row is 0, the second row is 2. Okay, another thing, well, I'll get to that in just a second. So this is good. This is a good thing to do. But an even better thing to do is if we want this to be a column vector, we know this dimension is going to be 1, we can put a -1 here. And the way that that this reshape function interprets that is it says, okay, well, I know that there needs to be 1 column, and then I'm going to make however many rows there in that for it to make sense. And so similarly down here. Okay, so now I'm going to run this again. Okay, so I didn't print hold on 1 second. I got rid of this, and then after the reshape, we're going to have this, v1, and again, we get this difference here. Now, another thing that we could do is we could say, okay, I want there to be 3 rows, and I want you to figure out how many columns are going to be. And this is also going to give us the same exact thing. But typically we want there to be 1 column, and let's say this is sort of a generic vector. We don't know how many rows or entries there are, so we're going to put a -1 there. Okay. And notice what happens when we do v1 plus v2 right here. Sorry, let me run this again. When we do v1 plus v2 again, it puts it in matrix form. That is column vector form like we're expecting. Okay, very good. The next thing that we want to do is v1 dotted with v2. Okay, so there's a number of ways that we can do this. So one way is just going to be np dot, and we can do v1 comma v2. So the dot function is a function in the NumPy library. This will give us a little bit about exactly what it does, what the dot function does. And essentially, if you put 2 different NumPy array there, 2 different NumPys array there, it's going to interpret the thing that you want it to be, basically. So in this case, it should give us the dot product of these 2, which is going to be 1 plus -1. Sorry, 1 times -1 plus 0 plus 0. So it should just be -1. Okay, so here's the issue with this. So what happens is that we give it 2 shapes, 3 by 1 and 3 by 1. So what it's trying to do is interpret what we want. But remember, this dot product is like matrix multiplication, and remember, matrix multiplication is only defined if the inner dimensions are equal to each other. Okay, so what we want to do here is the following. The dimensions of this is 3 by 1, and this is 3 by 1. So we need this to be a 1 by 3. So we can do dot transpose here. And this is going to give us the transpose of V1. So this is V1 transpose times V2. And so, or V1 transpose matrix multiplied times V2. And we're going to get this, which is minus 1. Now, notice the interesting thing here is the return is a 1 by 1 matrix, which is, just a scalar, but this is one of the things that we have. Okay, a better way to do this, though, is going to be V1 dot T and then at V2. So the at, when you're dealing with two matrices, the at symbol is an overloaded symbol, or it's a new operator that just means to do the dot product, or it means so this right here is exactly equivalent to what I had before, which was np dot dot. So we're going to run this again, and then again here we get minus 1. Okay, so the next one we're going to do this right here. It's going to be V1 times V2 transpose times V2. So if we do V1 transpose times V2, that's like the dot product. Like if that transpose is there, that gives us the dot product. But V1 times V2, this is a 3 by 1 matrix times a 1 by 3 matrix. And so the output of this right here is going to be a 3 by 3 matrix, and then we're just going to multiply it by V2. Okay, so now we're going to come down here, and we're going to have V1 at V2 V2 transpose, and then we're going to multiply this by V2. Okay, and if you compute what this should be, well, actually, yeah, if you compute what this should be, it should be 5, 0, 10, if I remember correctly. Okay, and that's exactly what we get, 5, 0, 10 there. Okay, now for the norm of V2, I could write a loop to explicitly compute the norm, but instead what we're going to do is use the norm function in the linear algebra package, the linalg package in NumPy. So np.linalg.norm of V2. Okay, and down here, W is equal to that. So now I'm just going to do np.linalg.norm. Okay, and I'm just going to put, this is my W, so I'm just going to copy and paste it here. Okay, we're going to run this. So the norm of V2, you can compute it, it's going to be the square root of 5. This is roughly the square root of 5. And the norm of W, if you compute it, should be 25 plus 100, 125. This is roughly this is the roughly the square root of 125 out to whatever precision that is there. Okay, so notice one thing that I did not do here. Notice that for a lot of this stuff, I could have written a loop in Python to compute these things explicitly. Whenever possible, and we're going to illustrate why this is in one of the things below, but whenever possible, we want to use the built-in NumPy functions like norm, this at symbol, and stuff like that to do the multiplication, because it's going to be able to take advantage of all sorts of algorithms and parallelization and all of the sorts of things like that just an explicit loop is not going to be able to take advantage of. Okay, so the second part, we're going to create these two matrices. This is D, this is R, and A is going to be equal to D plus R. And then it says use numpy.linalg.solve to solve this equation right here. Okay, so now what we have here, A is going to be, so A is the sum of D and R. So I've just sort of put a blank 3 by 3 matrix here. D is a blank 3 by 3 matrix, and R is a blank 3 by 3 matrix. So I'm going to actually move this down here and say A is equal to D plus R. Okay, and this tells us what all of the matrices are here. So D, there's a great way to do this. Creating diagonal matrices is something that happens a lot in NumPy. In Python. So here's what we're going to do. We're going to say there's a couple of ways that we can do this. Um, let's see. I'm going to say D is equal to NP. I'm going to do this first. I, 3. So I here means the identity. Okay, so when I run this code, this D matrix here is going to be the identity matrix. Obviously, that's not what we want. And so we get 1, 0, 0, 0, 1, 0, 0, 0, 1. And we want to multiply this by 2. Now that is going to give us what we want, 2 on the diagonal. Okay, so that's exactly what we give. Another way that we can do this, though, is diagonal. Hold on a second. So another way that we can do this, this is not necessarily the best way for this problem, but we can do 2, 2, 2, and this is going to give us a diagonal matrix of the appropriate dimension with 2's on the diagonal. So that's what we have there. I think for what we're doing now is going to be 2 times np dot I of 3 is exactly what we want here. Now for R, okay, for R, we're going to look at the following. So this isn't giving us a bad suggestion. So this is saying do minus np dot EYE. So I'm going to say np dot EYE. And here's what I'm going to do. I'm going to say I want the dimensions to be 3 by 3. And now I'm going to say k is equal to 1. So let's see what happens when we do this. Oh. Wait. Not sure why this is not working. Okay, there we go. I don't know what I was doing wrong, but anyways, man, now I'm having a hard time even seeing what's happening here. This is D. Oh, so notice what R is. So man, let's see. Whoops. So this this \n gives me a new line, and that's what I'm going to do so that it's a little bit easier to see. And it's actually, we can see it's going to be a little bit easier even if we do like this as well, to put new line characters there as well. That's probably what I should have done in the above. Okay, sorry about that. I have these things all planned out, and then I start to type them and problems happen, and I'm like, what's going on? And I'm never exactly clear what happens. But this is what happens when I teach live classes as well. But usually the students are like, hey, you did something wrong. Anyways, so let's notice what we have here. R right now. So this is what the R matrix is right now. But notice what I have here. np.EYE 3, and then k is equal to 1. Okay, so what this means is going to give me an identity matrix where the dimensions are 3 by 3. Or it's going to give me a matrix of dimension 3 by 3 when I say k equals 1, this tells me which diagonal I want the ones to be on. So if I do something like k equals 0, that's the main diagonal, and we see that R is just going to be the identity matrix. But if I do k is equal to 1, that's going to give me this means the diagonal is going to give me a 3 by 3 matrix, and the diagonal above the main diagonal is going to be the diagonal of all ones. So if I run this here, we see exactly what we get here. R 0 1 0 0 0 1 0 0 0. So those entries right there, the 1 and the 1 there, that is the diagonal above the main diagonal. Okay, but notice we actually have a -1 there, so we're going to do -1 times that, and then minus np.eye, and then 3, and then k is equal to -1. Okay, so -1 is a diagonal below the main diagonal. Okay, so this gives us R, and now we see A is exactly what we need it to be. Okay. Now, the B vector is this vector, so I'm going to make this into a vector. So I'm going to say this is equal to np.array 1, 2, that helpful thing is getting in the way. 1, 2, -1. You can turn this into a matrix like we did before if you want to. Okay, now the solutions, we are going to do np.linalg solve A, B, like this. Now, there's a way to do a matrix inverse, and so you could just do the inverse of the matrix times B, but that's not typically how we want to do things. We typically want to do things with this solve algorithm here. Okay, so we're going to run this. Great. Oh, I forgot to give it. I forgot to wrap it here. Okay. Man, this is going great. Linalg. Okay, finally. The solution to AX equals B is that right there. Now, let's say we wanted to do the thing where we did the reshaping, so we could say this, so right here, this is a NumPy array, so we can do dot reshape here, and we want there to be one column, so we're going to do -1 here. Okay, and now let me make this into a new line as well. And again, we're going to get 1.5 to 0.5, but written in the column way. But also, it's not just a vector, it's a matrix. So this is sort of a matter of taste at this point. In different settings, there's different things to do, or better things to do, I guess. But anyways, for now, it's just sort of a matter of taste. Okay. Let's move on to part 3. So observe that the matrix above is diagonal. Also recall that the inverse of a diagonal matrix, whose diagonals are all the same, so in other words, if your matrix is just a multiple of the identity, then the inverse is just to divide by whatever the diagonal value is. So D inverse X is equal to 1/2 X for this D. This D has 2 on the diagonal. Okay, in the cell below, we're going to let X naught is equal to the 3 by 1 0 vector, and R is going to be B minus AX naught, or the norm of B minus AX naught. So what's happening here is B, X naught is an approximation to the solution of this equation, AX equals B. That's what we're thinking about X naught. And B minus AX naught is the difference between, if X naught was a solution, B minus AX naught would be 0, and so the norm would be 0. And so the closer X naught is to an approximation to the solution, the closer this norm right here should be equal to 0, and R is called a residual. So use a while loop to iteratively, and I say, hey, that word is in the title of this course because what I'm introducing here is our first iterative method, right? So in the week 1 video, I said at the end of week 3, you'll be able to use an iterative method. Well, this is that iterative method. This is called the Jacobi method. We'll talk more about it later. This is a very simple method. Okay, so the xk plus 1 is going to be D inverse times B minus D inverse times R times xk. On each iteration, we want to compute this residual. and we want to do these loops until this residual is less than some tolerance, which here I'm telling you to make it 0.001. And then the condition to terminate the while loop is going to be when the tolerance is less, when the residual is less than that tolerance. And then these are the final two things to do. Print the final value of the final iterate, xk, that is the final approximation to the solution. The residual, b minus axk. The final rk value, that's going to be, the final residual, and the number of iterations needed. And it says we can use all of the normal vectors in NumPy. Okay, so here's what we're going to have here. All right, so let's just get the thing set up. So D is already the matrix that we have up there. So I'm going to say that tolerance is equal to 0.001. The x naught, I'm going to say is going to be equal to np dot zeros 3 by 1. Okay, so I'm already saying that this is going to be a 3 by 1 matrix. That's it. This is np.zeros gives you a matrix or a vector of all zeros of this given shape right here. Man, okay, and then it gives me the first residual here, which is np.linalg norm of b minus a times x naught. Okay, so remember this is the matrix multiplication. Okay, so now what I'm going to say, so I did not want that to have that there. Okay, so while r is greater than the tolerance, okay, so while, well, that's less than, so I really should do something like this. So while r is greater than or equal to tolerance, here's what I'm going to do. Instead of calling this x naught, I'm going to call it x, and you'll see why in just a minute. Conceptually, we kind of think about it as being x naught. Okay, x is going to be equal to, and we're going to use this formula right here, d inverse b minus d inverse r times x. Now, d inverse is just 1/2, so it's going to be 0.5 times, and then b, which is b, I didn't set my, as the same b vector up here, sorry, b minus r times x, so r x, just like that. And then r is going to be equal to np dot linalg dot norm b minus ax. Okay, and all right, so this is the update. So notice that even though we are iterating, we have the first iteration, the second iteration, we're just overriding the previous value, because for this assignment we don't need to keep a list of the residuals or a list of the x iterates. We just need to know the last one, so we're just going to keep overriding what we've done before, and that's exactly what's happening here. So xk plus 1, that is the new value of x, is going to be equal to d inverse b minus d inverse times rx, and that's exactly what we have here. This is the d inverse, and now we have b minus rx. Okay, so the final iterate, we're going to put x here. The final residual is we are going to put r here. Oh, sorry, no, the final r value is r. The final residual is is b minus ax. The idea is we want this to be close to 0, right? So the entries of this should be very close to 0. Definitely they should be less than whatever the tolerance is. And the number of iterations, we haven't figured that out yet, but let's just run this to see what we get. Okay, now we know up here this is the answer, 1.52 and 0.5. This is our approximation, so 1.499, 1.999, and 0.4999. So this is all within 0.001. This is the final residual. This is even being approximated at 0. And you know what? I'm going to put new lines here so that we can read these a little bit better. Yeah, okay, so this is the residual. It's approximating just at 0, you can tell. This is the final R value, which is the norm of the residual. The number of iterations. Okay, so what are we going to do here? So I'm going to make a new variable. Iters is equal to 1 because this is the first iteration here. Well, we'll start with 0. And then each time we go through the loop, we're going to say iters. We could say is equal to iters plus 1. But this idea that we are, taking a thing and updating on a loop over and over and over again, this happens so much, there's a special expression for it, plus equals 1. And this notation here, iters plus equals 1, just means iterations equals iterations plus 1. There's no, like in C++, you can do iters plus plus. There's nothing like that in Python. At least not this sort of defined. And down here, we're going to put the number of iterations. Okay, so we're going to run this again. The number of iterations is 22, which is kind of a lot of iterations. This is one of the problems with the Jacobi method, is that it converges somewhat slowly. And we can see if we increase the tolerance by a factor of 10, so make it 10 times as precise, we're going to need 29 iterations. And if we do this again, we're going to need 36 iterations, and so on and so forth. Okay, so I'm going to put it back to 0, 0, 1, which is what well, if we do 0, 1, 16 iterations, and let's see what it is for 0.1, just 9 iterations. Anyways, though those things are not necessary. Okay, I'm just doing it for fun, I guess. Okay. So what we're doing here below in this part is the portion where I want to illustrate why using Oh, yes, okay, sorry. I got the parts backwards. Okay, the matrix in the second and third parts, that is what we just did, has a special structure. The main diagonal is 0. The main diagonal is the main diagonal is 2. That's a mistake there. I should say the main diagonal is 2. Let me actually. You're gonna get to see me do a little work in real time here. I know it's very exciting, but I just want to make sure that I fix it for the homework assignment. The main diagonal is 2. Okay, there. Save. Okay, back over here. So the main diagonal 2, the diagonal above the diagonal is -1, the diagonal below the diagonal is -1. So using npi and or npdiag, make a matrix of this form of arbitrary dimension. In other words, it's exactly what we did it up there. So n is equal to 100. B is going to be a random matrix of a random vector of size n. I don't think we're going to use that for this. I think we're going to, well, oh no, we are. Sorry. All right. So M is the matrix. So, okay, so we want this to be the matrix that we sort of very similar to what we computed up there. So we're going to get np dot I times n. So 2 times that. This is going to give me an n by n matrix, an n by n matrix where the diagonal is equal to 2. And then we're going to do minus np dot EYE. Sorry, sometimes like when I am just writing code, well, all the time, essentially, when I am, basically all of the time when I am teaching for these online courses, there's no feedback at all, and it's much of a challenge. I'm just talking to myself. When I'm doing the coding stuff, there's even like details that my brain will just sort of skip over. So sorry about that. Okay. Luckily, it's a very easy fix because you compile the code or run the code, and if you've got something wrong, it's going to not work. So this is what we have here. N is 100, M is the matrix here. And it says below we want to compute the number of non-zero entries of the matrix M. And this says deal with the matrix M directly and do not use a special structure of the matrix to compute the number of non-zero entries. Okay, so for example, it's easy to see that there are this many non-zero entries from the definition of the matrix. What I don't want you to do is I don't want you to just say, well, the number of non-zero entries is in plus 2 times in minus 1, and just, you know, fill in 100 for in. I want you to deal with the matrix directly. And there are a number of ways that we can do this. So one way is just by using a loop over here. Hold on one second. So I'm going to do a loop over here. And what I'm going to do is the following. I'm going to say for k in range in, for j in range in, and I'm going to say if m of kj. Okay, so what is this? Well, m is a matrix, and if I want to refer to the entry in the kth row and jth column, this is exactly how we do this. So if this is equal to 0, then we're going to say num non-zero plus equals 1. Okay, so we're going to print that out here. Okay, so I'm going to run this now. The number of non-zero entries is equal to 9,702. Let's remember that. 9,702. Put that here. Whoops. Oh, times. And again, oh wait. Something. Oh, sorry. This is if it's equal to 0. This says if it's equal to 0, we add 1. I want the number of non-zero entries, so that's going to be not equal to. Okay, so this is why I like to test what I have. Okay. To make sure everything is working properly. Okay, so now what we're going to have here, we're going to have something like this. Hold on one second. Okay, so we're going to get 298, which is exactly what the previous thing got us, I think. Yeah, 298. Okay, just so this is just, you know, I have confidence of this formula. I just want to make sure that that this is, you know, just testing my algorithm. That's what we're doing here. Now the total number of entries in the matrix is n squared, and so the percentage of non-zero entries is going to be the number of non-entries divided by divided by n squared, which is what we have here. Okay. Now this is something that definitely works, but there is a built-in Python or a built-in NumPy function for this. So we're going to do np dot count non-zero of the matrix m here, and totally get rid of all of this, because again, whenever we have the chance to do something with a built-in NumPy function, that's what we want to do here. Okay, so now this is what we have. Okay, gives us the same exact thing. Oh, then I need to do, well, okay, maybe what I'm going to do is a little bit different than what I did before. So I'm going to have it like this, and I'm still going to put this num non-zero. Okay, so that's exactly what we get. So notice that the percentage here is very small. It's 0.0298. And notice what happens if I make this bigger. If I make it up to 1,000, the percentage doesn't stay the same. The percentage is going to go, you know, I just increased the size by 100. The percentage is decreasing. So the bigger the matrix, the bigger the percentage of zero entries, or the smaller the percentage of non-zero entries. And I could keep doing this forever and ever. I guess once you get up to a matrix that's 10,000 by 10,000, that is a huge matrix, and so it's going to take a little bit of time for this algorithm to run. This b vector here is also spurious. It is from a different iteration of the project, so I'm going to go ahead and get rid of it here. Okay. All right, and so all right, 0.00. Okay, again, something like that. So let's go back to 100. Run this again. So this is a sparsity diagram, and the white entries are going to be the entries where there is a 0, and the black entries are going to be the entries where there's not a 0. So it's a little bit easier if you look at this on a 10 by 10 matrix. So we're going to get something like this. Okay, and each kind of grid, going, 0, 1, 2, 3, so on and so forth. Like one of those blocks, like a grid in a piece of graph paper, is going to be black if the matrix is not 0 there, and it's going to be white if the matrix is 0 there. So, for example, we could come up here. If we get rid of the identity part, what we're going to have is just a matrix with 0 on the diagonal and non-zeros on the diagonal above the major diagonal and the diagonal below the major diagonal. And so this is now what the sparsity pattern is going to look like, right? This is the 0, 0 entry, or more commonly, this is the first row, first column. This is the first row, second column, right? That is 0 in the matrix. That's -1. This is the second row, first column, it's equal to -1. Second row, second column, that's equal to 0, so it's white. Second row, third column, that's equal to -1, so it's black. This is the second row, fourth column, so it's 0. So, okay, this is one way that we can sort of, again, look at the sparsity diagram. As we go on, when we're dealing with one-dimensional problems, most of our matrices, maybe all of them that we're going to see in this class, are going to be tri-diagonal. So the diagonal is going to be non-zero, and the diagonals above and below the diagonal are going to be non-zero. When we get to two-dimension, we're going to have more complicated sparsity patterns, okay? And the matrices themselves might not be symmetric, but like the sparsity pattern will be symmetric. Okay, so now we have come to the fifth part. The goal in this part is to show that doing explicit loops is going to take a long amount of time, and so we should really only use this @ operator and in general the sort of built-in functions that Python has. So here's what we're going to do. We're going to compute the vector here, and here's what we're going to do. We're going to say we're going to sort of go down y and compute it column by column, I guess. And so we're going to do the following so I don't like that it's telling me what to do. This kind of distracts me because I look at it, but sometimes it's wrong. But okay, anyways, for k, one thing that I want to change though, I'm gonna introduce a variable n. N is equal to 1,000 for now, and I'm gonna make this n comma n here. This is going to be in here, and this is going to be equal to in here. Okay, so K designates the rows and J designates the columns. For K in range in, whoops, good gosh. And then we're going to say for J, for K in range in, for J in range in. Okay, so the column is going to stay the same, and the row is going to stay the same, and we're going to go across the columns. So y1 of k is equal to y1 of k plus m of kj. So I always like to keep things consistent and have K represent rows and J represent columns, so I don't even have, if I can, so I don't even have to think much about, what's what. So then times x of the xj. Okay, right, because yes. Okay. All right. So now we're going to run this. Okay, so a couple things to point out. The difference is going to be 6.6 times 10 to the minus 12. That basically means we did this algorithm correctly here. But notice what happens. To do the loop, so let me explain, because I didn't explain what this is. Tick is equal to time. That's going to give us the time before we do the loop. Toc is equal to time. That's going to give us the time after the loop. And then T1 equals toc minus tick is going to give us the elapsed time. And similarly down here. So the time taken to do the loop is 2.82 seconds compared with 0.001 seconds. Okay, and so what we're going to do here, this is just going to be T1 divided by T2. Okay, so we're going to run this whole thing again. And then it takes 1,000 times longer to do the explicit loop than it does to do the @ operator, okay? So it's 1,000 times longer, and it's taking like 3 seconds, 4 seconds here. And then let's see what happens if I do 10,000. I don't even know if there's gonna be enough time for this to complete, because the matrix multiplication is an n-squared algorithm. So multiplying it by 10 should be multiplying the total amount of work done by 10 as well. So this should take somewhere around 28 to 33 seconds. Based on what we've seen so far, it should be sometime around between 28 and 33 seconds. I'm going to just let it run because I want to see how long it's going to take. And we have a sort of counter down here as well. And notice before the ratio was 1,000. It took our method 1,000 times longer than the @ method. Let's just see what's going to happen here. This is really exhilarating, I'm sure, to be watching this. This is actually going a little bit longer than I expected. Oh no, sorry. 300, I just did some bad math there, didn't I? It took us somewhere between 2.3 and 3.8 seconds. 100 times that is 300 seconds, which is dealing in the minute range. So, okay. Well, you know what? You do not have to watch this. You could just advance it on YouTube as well. I'm just going to leave it like this and let it go, just because it's so much fun. I do want to say, I will just say some non-mission critical things, but I do just want to point out, I can't remember if I said it in the beginning of this video or not. The labs are typically going to be like this. You're going to have a homework assignment every week. I'm not going to walk you through the homework each time, but what I am going to do is walk you through a lab that has similar questions to it. Obviously, a lot of this stuff here is just to sort of get your feet wet with using NumPy and stuff like that. But I fully expect that when you're doing the homework problems, you're probably going to have to Google things or LLM things to try to figure out which Python packages you need to look at, what the issues are with things. You've seen me having issues here tonight just because, that's how things work sometimes, right? I make the homework assignment. I do the homework assignment just to make sure everything makes sense, and then I do a video of me doing it, and then sort of things kind of fall apart there. Okay, but I'm just gonna let this go. Now I'm realizing that 300 seconds is like 5 minutes, and I probably shouldn't let it go. So I probably will at some point zoom this up in the editing. So that took about 5 minutes to run. This is the total seconds to do our algorithm, and then this is the time taken using the @ algorithm here. And now, okay, if we think about this is a matrix where it's a 10,000 by 10,000 matrix, and we can see how long it's taken to do this. Now, this is not, we will see in practice, you see matrices that are this big, and with iterative methods, we are doing these matrix vector multiplications over and over and over again, sometimes thousands of times. So a matrix vector multiplication that takes that long to do is definitely not going to work, and even one that takes this long that's also not going to be something that is practically feasible. So lots of times, one of the reasons that iterative methods work is because the matrices are sparse, and if a matrix is sparse, there are special algorithms that can do the matrix multiplication much faster. Okay, so that is the end of the lab for tonight. I don't know. Please let me know if I can do anything better for the labs. This is the first time that I have done a lab in an asynchronous format like this. So I don't know if there's a better way that I can do it instead of just going through the assignment or something like that. I cannot do something like just teach you programming principles from the ground up. You're supposed to have known some of those things coming into the class. But and then if you don't, that's fine, but that's just something that you're going to have to think about on your own. But if there's better ways that I can sort of explain this or do something different, I don't know. I'm all ears, and I'm sure I'll sort of modify some of this stuff as we go along.